Hello everyone, my name is Vipin Abraham. In the previous video, we talked about superposition principle and we did a numerical based upon that. Today's video is just a continuation of what we did in the previous class. So in today's video, we are going to talk about dielectric constant. As you can see, there's a question. The question says, define dielectric constant of a medium in terms of force, right? Okay, let me just write the answer of this question and then we will try to understand what the answer means. Alright, so let's get started. Okay, so first, dielectric constant is represented by the symbol K. Now, some people write it kappa, some people write it K, but it doesn't really matter because you guys have to just first write it that you're talking about dielectric constant in somewhere in your answer sheet, so that will be fine, right? Okay, so dielectric constant K in terms of force is actually a ratio of force in vacuum divided by force of interaction in some medium. Okay, so let me try to make you guys understand what does this ratio thing mean. Okay, so you guys can see over here there's a definition. Let me just read it out. It is defined as the ratio of force acting between two charged particles separated by some distance in vacuum to the force acting between the same charged particles separated by same distance inside medium. Now what does that mean? We have studied that by Coulomb's law, if we have two charges, let's say Q1, Q2, and they're separated by some distance R, and let's say the medium is vacuum. The medium is vacuum, right? So we know the force of interaction comes out to be K Q1 Q2 upon R square, right? Very similarly, so this is that force, that is force in vacuum, right? Force in vacuum, let me call it vacuum, and this is some medium, right? Now in the second case, we are talking about the same charges and they are separated by same distance. The only difference this time here is, instead of vacuum, I have a medium. The medium can be anything. It can be glass, it can be water, it can be metal, whatever medium you want to take it, right? So the moment you introduce a medium instead of vacuum, the force of interaction will not be same as the previous one, because we have studied in the Coulomb's law that your K, this constant, depends upon the medium, right? The moment you change the medium, the force of interaction also changes, right? This time a different force of interaction will be there, and instead of K you can write it, K dash this time, yes, Q1 Q2 upon R square, right? So this is this force due to some medium, right? So dielectric constant is actually a ratio of force of interaction of the same charge with which they are separated by some distance in vacuum divided by the same charges, they are separated by same distance, but instead of vacuum you have some medium divided by the medium. That is what dielectric constant is, right? So okay, it's okay. I hope you started to get a feel of it, right? So it is saying over here that the K for water is actually 80 and dielectric constant for metal or a conductor is actually infinity. So let's try to understand what does this mean. Okay, so we just studied that K is actually the ratio of force in vacuum divided by force in some medium, or I can also write this thing as, I can write force in some medium can be written as force in vacuum divided by K. So basically what this expression is telling you, the moment you introduce a dielectric, a material or a medium, right, the force of interaction is reduced by this factor K. Now it depends upon the material in which you have inserted in between, right? Depending upon that material, the force of interaction will be changed. I hope that is understandable. Okay, let's take an example. Okay, let's take an example of water itself, right? So we have water, right? So you have a charge Q1, you have a charge Q2, right? So when vacuum was there, let's talk about vacuum here, vacuum. So when vacuum was there, force of interaction was coming out to be K Q1 Q2 upon simply R square, right? Very simple, right? Okay, the moment the water is introduced in between, right? So basically let's say there is water in between. Let me use blue one. There is water in between, right? Same distance is there The only difference is that instead of vacuum, I have water this time, right? So it will be changed. F dash will be simply is equals to F upon K, depending upon based upon this equation, right? So F dash, that is the new one, will be simply F upon K. K is what? For water it is 80. So you guys can see the new force of interaction will be reduced, will be divided by 80. That means it is being reduced in 80 parts. I hope you guys are getting it, right? Let's say the force of interaction was 80. Now after water is introduced in between the charges, the new force will be actually 1, right? So it is being reduced by 80. I hope you guys are getting it, right? Very similarly, if I talk now, instead of water, let's say if I introduced a metal, let's say a metal is introduced in between. If a metal is introduced in between, then what is going to happen? F dash, that is the for metal, right, will be F upon infinity, because see the value of K for metal or a conductor is actually infinity, which we guys can see over here. Yes or no? So the force of interaction, new force of interaction will be actually 0, because 1 upon infinity is actually 0, right? So I hope you try to get a feel of it, right? The moment you introduced a medium, the force of interaction will be reduced by the factor of K, and that factor K is what you call as your dielectric constant of that particular medium. I hope that is understandable, right? Okay, let's move forward. Okay, now here you have another question. The question is asking you, show that K is actually your dielectric constant is actually equals to epsilon upon epsilon naught. I hope you guys remember what was, okay, you guys can see over here, this K is actually your dielectric constant, right? Okay, what was epsilon, right? If you guys remember correctly, it was permittivity of medium, right? And epsilon naught was permittivity of free space. We are actually talking about vacuum, right? So epsilon refers to permittivity of any kind of medium. Epsilon naught represent the permittivity of vacuum, or you can also call it free space, right? So I have to prove this relation. It's actually very simple. Why I have taken this? Because this is a favorite board question. There are a lot of times board has asked this question, right? So let's try to answer this question. How we are going to do this one? Very simple. First, let's talk about any two charge particles. Let's talk about medium first. So let's talk about vacuum first. Okay, so when you have vacuum, you have a charge q1 and you have another charge q2. They are separated by some distance, let's say r. Okay, right. Okay, now the force of interaction between these two, obviously this charge q1 is going to experience this repulsion because of q2. This charge q2 is going to experience a repulsion. This will be fq2 because of q1, right? So you have to find out this force of interaction. This force of interaction will be simply written as k q1 q2 upon r square. This is something which we all know. Now you can also write this k as 1 upon 4 pi epsilon naught. Yes or no, right? Because we're talking about vacuum, right? Okay, so I can write this f is equals to q1 q2 upon 4 pi epsilon naught times r square. This is my first equation. I hope that is understandable, right? Very similarly, let's talk about any medium. Let's say instead of the same charges we are talking, they are separated by same distance, but this time I have a medium in between, right? So let's say I have the same charges q1 and q2, they are separated by same distance r, but instead of vacuum I have a medium this time, right? Again, force of interaction q1 because of q2, force of interaction on q2 because of q1, right? But this time the force will be different, f dash, right? F dash will be equals to again k dash. K is also different, right? q1 q2 upon r square, or I know this time K dash can be written as 1 upon 4 pi epsilon instead of epsilon naught. Epsilon, that is the permittivity of medium, right? So I can write it Q1 Q2 upon 4 pi epsilon times of r square. This is my equation number 2. And we all know that K is defined as the force in vacuum divided by the force in any medium, right? So all you have to do is the force in vacuum, the force in any kind of medium, right? All you have to do is just divide these two. So when you divide it, you will get Q1 Q2 upon 4 pi epsilon naught times r square multiplied by 4 pi epsilon r square divided by Q1 Q2, right? So you guys can see Q1 and Q2 will cancel out, 4 pi will cancel out, r square will cancel out. The answer comes out to be K is equals to epsilon upon epsilon naught. I hope that is understandable. Yes, right? So this is how you can prove K is equals to epsilon upon epsilon naught, where epsilon is your permittivity of medium, epsilon naught is the permittivity of free space. I hope you understood it. I hope all of you are doing good. Stay home, stay safe.